In this video, I want to talk about the slope of linear equations. Before we talk about slope, I first want to review what the basic shape of a graph of the form y equals mx plus b looks like. In other words, I want to look at a linear function. And as an example, I have this graph y equals negative 2x plus 1. I'm asked to evaluate for all the x values, so essentially I'm going to plug in x, get y values, plot those points, and then sketch the resulting graph. So the first point I'm asked to plug in is the point negative 2. So I'm going to do y equals negative 2 times the x value, negative 2, plus 1. And since negative 2 times negative 2 is a positive 4, plus 1 is 5, I get the first ordered pair, negative 2, 5, which I can plot in the graph by going left 2 and out 5. If I continue, the second x value is negative 1, so plugging in I get y equals negative 2 times a negative 1, which is positive 2, plus 1, which gives me a y value of 3. So my second point is telling me to go left 1, up 3, giving me my second value right about here. The third value of x equals 0 I can plug in. This tells me to do y equals negative 2 times the x value of 0, which is 0, plus 1 is 1, giving me the third value, 0, 1, telling me to go left and right 0, and then up 1. So here's my third point there. For the fourth x value, I'm asked to plug in x is 1, giving me y equals negative 2 times a positive 1, which is negative 2, plus 1, which is a negative 1. So my fourth ordered pair is 1, negative 1. Going right 1, down 1 for my fourth point here. And then finally my last point is 2 for x, so plugging in 2, I get negative 2 times 2, which is negative 4, plus 1, which is a negative 3. Meaning my final ordered pair is 2, negative 3, so right 2 and then down 3 puts me right here on the graph. So now what we recognize and what I wanted to review before we started is that the basic shape of this graph is a line. In other words, this y equals mx plus b graph does have the basic shape of a line if I connect all these points, which looks something like this. Now the new idea that I want to talk about though is the slope of this line, because we're going to notice as time goes on, plotting these points one by one can get harder and harder. The values become less and less easy to work with as they become fractions. So we want to come up with other ways of looking at the basic shape of graphs. So this is where slope comes in. And the general description of slope is that slope, or what we call the value m, is the rise divided by the run. And we notice here that rise, our rise value, is simply the change in the y, or in other words, how far we're going up or down. Meanwhile, the run is the change in the x. So I have this diagram off to the side here. I notice that if I just pick a point, such as 0, 1 on this graph, and if I then slide off to the right, and if I then slide up, I notice that the rise versus the run is relatively easily to compare. It is 3 to 2. So again, comparing this, the run is 3, which I can then write in. So run is equal to 3. Meanwhile, on this graph, I notice that the rise, the change in y, is 2. So if I write this in, I can see that the slope of this equation is a rise of 2 over a run of 3, or in other words, 2/3. And notice that for a line, this is continuous. Whether I talk about from going to 1 over to 3, and then from 1 up to 3, a rise of 3 versus 2, I again see the run of 3 and the rise of 2 again happening later on the graph. So the first thing we want to do is just practice finding the rise over the run. We can do this quite simply just by looking at the shapes of graphs. So first, if I look at this, I already have 2 points identified. If I first move over from this point 0, 1, I notice that my distance in the x direction is basically giving me a run of equal length 1. So if I'm going to start talking about the slope, write the general equation here, the slope of any line we just discovered was equal to the rise over the run. And we just discovered that the run of this equation was equal to 1. So now all I need to discover is the rise, the change in the y. And if I sketch this in, I can notice that I'm going in the positive vertical direction. So notice I am moving up, meaning my rise is equal to 2. And I'm going to make sure that we emphasize that that is a positive 2. This is important to note because it is possible that I could be going up or it could be going down relative to the run. So we want to emphasize that the rise here is in fact a positive 2, meaning that the slope simplifies to 2 over 1, or in other words, the slope here is just equal to 2. So if we try another example, again I want to calculate rise over run. So it really doesn't matter where we start. I can pick either the rise or the run. I notice that if I pick this first point, negative 1, 4, the first thing I notice is that I am going down 2. Now since this is down, I want to emphasize here that the rise, it is still a rise because we're talking about vertical, but it is now negative because I'm moving in the negative direction down 2. So that my rise here would be negative because of that movement down. My run, however, if I sketch this, I'm now moving over to get to that other point that I've identified here, 3, 2. My run here is equal to 4. So the run is equal to 4. And now that I have the rise and the run both identified, all we have to do is set up our slope equation. So I notice here that slope is equal to the rise over the run. So rise over run. And if I set this up, since my rise is negative 2 and my run is 4, I can simplify this if I want to. And that would simplify to negative 1/2 as our final rise versus run. Now we can also check this. I had negative 2 over 4. Is it also true that I could have gone down 1 over 2? Well, let's check this. If I just went instead down 1 and then over 2, does this also work? And see how that puts me right back on the graph. So I can see that negative 1 over 2 is just a simplified version. And in fact, if I did that twice, the negative 1 down 1 over 2, it's actually equivalent to the original rise over run, 2 over 4, which I just found. So now I don't have these predetermined points. So when I'm trying to find a slope on a graph like this where I don't have points jumping out, I like to immediately just try to identify points on the graph where it's a very clear intersection point. So for instance, I notice that negative 2, 1, I have this really clear, obvious point that intersects. And then also over here at 1, 3, I see this other clear point where it's right on the integer line, exactly over 1, exactly over 3. I want to avoid points like this, where it's in between 1 and 2, and I really can't tell exactly where the intersection is. We want to make easy numbers to work with, so picking these nice values. So now if I'm going to try to find the slope, just as a reminder, slope is equal to rise over run. So I am being asked to find first the rise or the run, doesn't really matter, but I have to find both of these for this given graph. So either one's fine. I can start with the run. If I move over, I notice that I have a rise, or rather a run rather, because this is horizontal. I notice that I have a run equal to 3. Or in other words, I'm moving horizontally to the right by 3. So now I need to look at the corresponding rise, and since I'm moving up, I can note that the rise here, first of all, was positive, and it's a positive 2 because I'm going up 2. So then my slope, or my rise over my run, I can very quickly calculate that the rise was a positive 2, the run was a positive 3, So then my overall slope here is going to be 2 over 3. And again, if you wanted to check this, see if this still works, I can even carry this on further. If I went over 3 for the run and then up 2 again, does that put me back on the graph? And I can say yes, that's still putting right back on the line, so that slope does seem to check out. So one more quick problem here. If I again identify two good values, and when I say good values, I mean values that are easy to see on the graph here, I notice that I do have one right here at negative 2, 2. That's a clear point that I can use. And it looks like I might even have to go all the way to the very end of the line here. But I can find another pretty clear point right here at negative 4, negative 5. So now if I'm going to try to find the rise over the run, again, it doesn't really matter which one I do first. If I want, I can do the rise first or the run first. I'm going to draw the run here. So I can see that since I'm going to the right by 2, that my run is equal to 2. So if I've already done the run, that means I now need to do the rise. And I'm going down, so I automatically know that if I'm talking about the rise, it's going to be negative because I'm going down. And that's going to be a negative 3 because I'm going down by 3. So now if I talk about the slope of this equation, which is again always equal to the rise over the run, since I found that the rise here was negative 3, and since the run was 2, I can see that the general slope is negative 3 over 2, or in other words, down 3 over 2. And I can check this again if I want. I go back to the graph, and if I go with a rise of 2 and a run of 3, I notice again I do go right back onto the graph, so that slope seems to check out. So now a second way we can find slope, they don't always have a graph to go by. I can also just simply use 2 points. So very simply, I can find the slope of a given line without the complete graph as long as I know those 2 points. And I notice that those 2 points here I can call x1, y1, and here I can call this set x2, y2. So all I have to do then is simply calculate the slope. And the good news is that the rise is just the difference in our y values. Notice if I take y2, this top point here, and I take away the distance from y1, that's going to give me my vertical y value. And for my run, if I just take away x2 from x1, or again, subtract the x distances, that will give me my run for the slope. So let's see if we can calculate a few slopes of these lines here and confirm that this makes sense. So again, first we want to find the slope, and then we want to actually plot the points and just check our answer by sketching it out. So first, if I have negative 5, 1, and 1, 4, the first thing I always like to do is label these as x1, y1. Doesn't really matter which one you do to which, but just labeling is going to make this a little bit easier. So x1, y1 for that first one. I can call this x2, y2, and now I just have these things clearly labeled. So we just discovered, or at least we are hypothesizing, that the slope is still the rise over the run. So rise over run. And we found that the rise was quite simply y2 minus y1, or in other words, the change in y over the change in x, so x2 minus x1. So if I plug in, the y2 value I have is 4, which I can see right here. Here's my y2 value. And then the y1 value is 1, which I can see right here. Here's our y1 value. Over, I want to do the run. x2 is 1, which I see right here. x2 of 1. And then I want to take away the x1 value of negative 5, which I again can see sitting right here, the x1 value. Now notice how I did minusing a negative. So all I need to do now is simply simplify this. So if I subtract 4 minus 1, that gives me 3. And if I do 1 minus a negative 5, that gives me 6, which can then simplify into a slope of 1/2. But again, we don't want to just take this for granted. Let's actually confirm that this is true. So if I plot these points on the graph, my first point is left 5 up 1, or in other words, negative 5, 1, which puts me right here. My second point is at right 1 up 4, which puts me right here. And I want to confirm that if I have a rise of 1 compared to a run of 2, that this is in fact the slope of a line between those. So let's test this out here. I'm basically just going to keep tracing with a rise up 1 over 2, and I want to see if this actually connects our 2 points. So up 1 over 2, and if I do it 3 times, I actually find that yes, that puts me directly to the next point. So this is in fact the slope between these 2 points. So as another example, let's go through this problem. Again, I know that slope is equal to rise over run. So rise over run. And I can find that rise by taking away the difference of the two y values, y2 minus y1, and the run's the difference of our two x values, x2 minus x1. And I can label those right here if I want. Let's call this x1, and then the 6 will be our y1, and then the 2 can be our x2, and the negative 3 can be the y2. So now all I really need to do is plug these in. So I'll come down here. If I plug in the y2 value, which was negative 3, I then need to subtract the y1, which was 6, over, and it looks like the x2 was 2 minus a negative 4. So simplifying, that looks like I get negative 9 over a positive 6. Make sure you watch out that subtracting a negative is really adding the 4. And this, if I divide both by 3, can actually simplify down to negative 3 over 2 for the slope. Again, we can confirm this by actually plotting the points. So if I go left 4 up 6, that's going to put me right about here on the graph. And then the second point, 2, negative 3, I'm going right 2, down 3. I want to confirm that if I continuously go down 3 over 2 for our rise over run, that I'll get to the next point. So let's see. If I go down 3 for the rise, over 2 for the run, do it again, down 3, over 2, and then one more time, if I go down 3 and over 2, I can see that I do get to that next point. So then one more quick example. Again, we're going to find rise versus run. So I recognize that rise over run is our slope here. So I can set up rise over run is equal to, the rise is our difference in y values, y2 minus y1, over x2 minus x1. And if I label our points, I can call negative 6x1, 3 can be our y1. And then how about we call the 4 here our x2 and the negative 1 our y2. I can simply plug in here. So y2, that looks like negative 1 minus the y1, which is 3, all over x2, which is 4, minus our x1, which is a negative 6. And since I'm subtracting a negative, I'm really adding. That's going to give me negative 4 over 10, which should reduce to negative 2 over 5 for our slope. And again, one more time, we just want to confirm this. I'm going to plot the points and make sure this works. So my first point is left 6 up 3. My second point looks like it's right 4 down 1. And I want to make sure that if I go down 2 over 5, that I do in fact get from one point to the other. So if I start at this first point, if I go down 2, going left to right, over 5, that puts me right here to the negative 1. And if I go again down 2 one more time, and then again right 5, I can see that I do get perfectly from one point to the other. So we've looked at two different ways of finding slope. First, by just looking at the graph. The second, by using the slope formula given 2 points. The third way is that we can actually just look at an equation. And what we find is that if we solve a linear equation for y, or in other words, if we get it in the form y equals mx from plus b, we actually find that m is very simply the slope of the equation. Now, one thing I want to emphasize down here is that this is only true if the equation is solved for y. It's very specifically only in this slope-intercept form, which we're going to talk about more. But if I'm going to find the slope, it has to be that m value times the x, which is only true when the equation is equal to y. So let's try a couple examples here. These first two are pretty simple. I can already see here that this equation is already solved for y, or another, both of these equations are already in the form y equals mx plus b. So if I write this right below, y equals mx plus b, I'm just looking for that slope or the m value. Remember, the m value is that value here that's being multiplied by the x. So if I look at my equation, it should hopefully jump right off the board here that the negative 2, this negative 2 right here, is in fact our slope. And it's that simple. If I have it solved for m, I'm just looking for the value that's being multiplied by x. So rather, if it's being solved for y, which it is, I can look at the equation. I can clearly see that y is by itself. It's solved for y. That means that the m value is the slope. So quite simply here, I can just say that the slope is equal to negative 2. Right? That's our m value being multiplied by x when the equation is solved for y. So coming over to this other equation again, it's already solved for y. Y is already by itself. Again, I'm going to write y equals mx plus b. And the question is, well, what's m if there's nothing there? Keep in mind, I can always imagine that anything is being multiplied by 1. So I actually would imagine here that our slope is simply equal to 1. And we'll see this more in the future when we talk about graphing this y equals mx plus b form. But for now, we'll just settle for finding the slope. So one more type of problems. I notice here that the equation is not solved for y. If I look closely, I have y, yeah, but I also have this 3x. So before I can find the slope, I actually need to solve the equation for y. I'm going to do this by subtracting 3x from both sides. This is going to give me that y equals negative 3x plus 5. Now that this equation is very clearly solved for y, I can write the y equals mx plus b form right below it. We're looking for the m value, that value multiplied by x, which is the slope. I can see that right here. There it is, it's the negative 3. So quite simply, I can just say, well, the slope is equal to negative 3. And just to emphasize this, it's not positive 3. Right? If we looked at the original equation, I had this positive 3 sitting right here. But until I actually solve it for y, or in other words, until I get y by itself, it's not in slope-intercept form. Once I get y by itself, I actually see that it's negative 3. That's the slope, not positive 3. So then this last problem over here, again, I notice that y is not by itself. I need to get y by itself by dividing both sides here by 2. So if I divide both sides by 2, I get y is equal to, I can keep that 3 divided by 2x. The 4 divided by the 2 is 2. So now if I compare this equation to the y equals mx plus b, I can see y is by itself. So I'm looking for the m value, and here it is right there, 3 over 2. So this tells me quite clearly that the slope here is equal to 3 over 2. So I now have some problems for you to try on your own with all 3 different methods based on graphs, based on points, and based on equations, practicing to see if we can find slope. So try those problems, and we'll check on this next class.